I'm involved in the IYPT 11 years already, and I have the honor to play the role of the chairing juror. So we first start with introducing the jury members. We have 5 of them playing the regular jury role and also 2 first-time jurors. So I would like to kindly ask our jurors to introduce in the order that we are sitting. So go ahead, Frank.
Hi, I am Frank Smuts from the University of Cape Town. I am currently a doctoral candidate in mathematical physics, so I will be especially focused on theory, but looking forward to seeing your work.
Thank you so much. Hi everyone, I'm Apostolos from Greece. I wish you all good luck.
Hi everyone, I'm Sam. I'm a local juror, though it's my 3rd time as a juror at the IYPT, and I work as a laser engineer.
Thank you.
Hello, I'm Bill McWaters. My first year at IYPT was 2016. I'm team leader for Team USA, and please take it easy on them if you see it later in the
Thank you.
Hi, I'm Manila from Austria. I'm a teacher and university teacher for future elementary school students. I've been a juror before in IYPTs, but now I'm first time in the role of proud team leader of Team Austria. And yeah, I like all your countries. I appreciate the hard work of Team Kazakhstan. It's amazing people there. Special heart to Sweden for culture and for the correctness and the way of presenting. I really appreciate the debate. Thank you very much.
Thank you so much.
Hello, I'm Nika. I'm the first-time juror from Georgia. I'm also a team leader of Georgia. I'm a former participant. I've been participating 3 times. Now I'm doing my master's and PhD in University of California, Irvine. Wish you luck.
Okay, thank you. That's jurors. And then that's the time for introducing the teams. So we would like to start with Sweden.
Yes, hello, we're Team Sweden. My name is Gaveshna, this is Jessica, Basan, Astrid, and Adam. And here because we have our mascot, Linda. We wish you all a pleasant Christmas.
Okay, then the team Kazakhstan.
Hello everyone, my name is Yes, and this is my teammates, Anya, Aina, Sultan Murad, and Jahar. And as a tradition, we usually, when we come to the IYPT, we give as gifts for everyone, for jurors and the teammates, and we would like to share you some chocolate.
If we can keep this for the very last moment of the fight, that will be perfect, okay?
Okay.
Thank you so much. That was the... and then Hong Kong, go ahead.
So I'm Jaden Wong. This is Lucas. This is another Jaden. This is Kiro, and this is Yan. So nice to meet you all, and we are looking forward to a very fruitful business. Thank you.
Thank you so much. So let's proceed. So you already checked that your machines are working. I just would like to remind you that we are using the one projector over there. So you have to change the connection smoothly to allow any other teams to present what they have to present. The clock is over there. We have also a marvelous fight assistant. So if you could also say a word. So
Hi, I'm Max and it's my 3rd IYPT, but first as a flight assistant, and I wish you all the best.
So in case of any troubles, he will just assist you in this connection to make sure that everything works and we do not waste time. So we are about to start the first round, and in that round Sweden will be playing a role of the reporter, Kazakhstan will be playing a role of the opponent, and Hong Kong will be reviewing your work. So it looks like everything is ready to start. So only final reminder, we do not use any internet connection. There is no allowance of any third-person communication during the fight. Please remember, if you use any of the AI assist, you just have to simply show and tell us what was done by that. And then it's time to ask opponent to call the reporter for the problem. The time is on.
So Team Kazakhstan challenge Sweden team of opponent number 3.
We would like to accept. Yes.
Okay, so number 3. So we have 4 minutes to prepare.
Please write down the reporter's name.
Yes, and of course you write the reporter's name and the reviewer name and the opposer name on the whiteboard over there. Please remember to
Do we have all?
Upper than that.
Do we have any clicker we can use?
Yes, it's right. Yes.
Yeah, okay, yeah.
Thank you.
There you go. Okay.
Okay, you can start, but I would like to advise all the teams that please remember to be quiet to allow people to work, okay? Do not disturb others. Okay, so if you are ready, the time is on, go ahead.
Sorry, my name is Alan and I want to tell you something problem number 4, ringtone. The problem question goes as follows. If you, when a falcon ring falls from a certain height into the water tank, it generates a fountain and shoots water high into the air. How does the maximum height of the fountain depend on various parameters? Now, there are a few keywords in this problem formulation that I would like to go over. Namely, flat and ring, meaning that this is a ring that we're dropping in with no curved edges into water. And water introduces no viscosity, buoyancy, entrainment, and surface tension. Fountain tells us what we're looking for, a water jet being propelled upwards. The maximum height and parameters ask us how we can vary the different, how we can vary the ring to influence this maximum height. Now, here's a demonstration of this phenomenon. So we'll see a instantaneous first jet being propelled upwards with a secondary jet propelled upwards after an annular collapse. Barcode collapse, sorry. So in this presentation, I'll be going over a basic explanation of this problem, theory, experimental setup, and finally results and a conclusion. So when the ring impacts the water, it is only the annular area which comes in contact with the water. So the water that comes in contact with this ring has has basically two ways to go, either outwards, creating a sort of coronal splash, or inwards, generating a sort of focusing, which is the primary cause of the first jet. Now, since these rings aren't curved, these sharp edges cause shearing in the water, creating vortices, which in turn leads to added speed and added upward flow for differential, which could contribute to the maximum height. Now, the second jet that I talked about with the annular air cavity collapse might sound familiar to a Worthington jet, which is basically, so if you drop a flat disc into water, an air cavity forms, and when that cavity collapses, it generates water spikes, which is a Worthington jet. However, this problem does not describe a Worthington jet, as there is a water column in the middle caused by this inner hole of the ring. And this generates, so the rate of flow inward was redirected axially, instead causing a fountain being, the second fountain to be a sort of ring, circular rim shape instead of a focused jet. And our simulation confirms both of these jets, the first jet coming from the inward focusing, and the delayed second jet from the annular cavity collapse, redirected by the inner water column. To describe the regime in which the system is in, we will use the Buckingham tie theorem, which tells us how many dimensional groups we will need to use to describe a regime, basically. So our parameters are the thickness of the ring, the inner radius, outer radius, the surface tension, dynamic viscosity, density of water, gravity, and the initial velocity. And this, together with three fundamental dimensions, we find that we only need to describe 5 dimensional groups in our problem formation. These being the Reynolds number, the Froude number, Weber number, the thickness to outer radius ratio, and finally the radius ratio itself. Now, to describe the first jet, we split this velocity field into 2 components, as per the Henkel decomposition. So we have a first irrotational velocity field and a added rotational velocity field. Now for the irrotational term, we assume irrotationality as well as incompressibility, which leaves us with the Laplace equation. This Laplace equation, considered in cylindrical coordinates, becomes as follows. And the standard Henkel representation of this function phi, which is our velocity field, would be as follows, which expresses the potential in terms of zero-ordered Bessel functions with coefficients a and k. Differentiating this potential on z gives us the basically the launch speed of this irrotational flow and contribution. However, this integral exhibits here cancellation at the center. So to account for this, we are introducing coefficient CG of a fitted parameter that we will evaluate experimentally, which is a constant dependent on the ring's parameters. So we find a final formula for the rotational contribution of the first jet speed. Now for the rotational term. So to find out the effective velocity of this form, we use the impulse. We find this using impulse. And solving for Vf, where the added mass caused by the water that this ring is pushing along with it, gives us, this added mass function, gives us an effective velocity of as follows. And we get a final formula for the speed contributed by the rotational term. Now for the rotational term, we look at the circulation gamma I, which scales with the initial speed times the thickness of the ring, and from corresponds to the self-induced propagation speed, this one. we get a vortex ring sitting at a depth of ZV. And with an application of the Biot-Savart law, we find a rotational term contribution of as follows in this equation. Now, we get a final first jet formula by implementing these two contributions into the ballistic jet formula for the height. And we get a final formula for the first jet. Now on to the second jet formula, so we believe that the height would be the angular, the cavity depth times some sort of geometric focusing called by the range of parameters. So we first investigate how the cavity depth relates to the different parameters. So we introduce a time scale in which this cavity collapse occurs. And this initial cavity depth would be we approximate as the initial jet speed times this time scale. And with approximating V0 to the with this equation, we find a first order depth equation. But however, since the ring has a thickness, we have to add that as a minimal depth. So we get a final equation for the depth of the cavity. So, to consider how this affects the maximum height of the jet, we look at the energy that is contributed by this angular cavity collapse. So taking the average pressure over the cavity, along with and imposing it over the volume of the air cavity, we get the energy contributed from the air cavity collapse as follows. Now, since there are lots of losses in our system, one example being wave fluctuations in our tanks, we introduce a effectiveness constant, HKG. And so the speed contribution by the second jet would be the kinetic energy of the water times the our potential energy that is then converted into this speed. And we get a final formula for the speed, which we then implement in our ballistic formula once again, and we find a second jet formula. Now on to experiments. This is our experiment setup as follows, but it might look a little unclear in this picture, so we use a diagram instead. So we have a spring release system, where if we release the tension in the system, we found we allowed the ring to fall controllably and stably down to water without any obstructions, and the jet did not experience any obstructions either. So for the parameters in our system, we vary the ring dimensions, such as the inner and outer radius, the thickness of the ring. We vary the drop height, the different tank dimensions to see how that would affect the system, as well as the mass of each ring. And the control parameters were the water density, viscosity, and surface tension, all given by water. And for each round, we measured the first and second jet height. So these are our areas in our system. The biggest one being the measurement of the jet height, as we use a video camera to measure the jet height, which introduces parallax errors. But as we will see in our results, these errors are minimal. So to describe the regime, we use these dimensionless numbers that we introduced in the beginning, namely the Fresnel number on the x-axis, the Weber number on the y-axis, and the ground number on a color gradient. And we see that they all fall in this top right region, meaning that there are little to no viscous effects in our system, little to no surface tension effects, as per the Weber number and the Reynolds number, and the Fresnel number being about 10, mean or around 10, gives us that the system is in a supercritical flow. So our assumptions for this problem are given by this. So to look at how our experiments on theory correlate, we use a parity plot where we plot our measured points on the x-axis and our predicted points using our theory on the y-axis. And for the first step, we find a nice correlation where all of our points sit very quite closely to this 1-to-1 perfect ratio that we expect to find, giving us a clear experiment to theory correlation. For the second jet, we find a similar correlation, giving us that our theory holds true to reality. Now, looking at the jet heights of the first and second jet, we find that the first jet is consistently higher than the second jet, meaning that with our groundwork, we will now focus on the first jet impact and how that affects the maximum height, as that is what we're looking for. So for our formula for H1, we expect a great correlation between V0 and the jet height as it scales exponentially. And we find a nice correlation on this line with V area. We also find that a greater outer radius to inner radius ratio also gives greater first jet heights. And experimentally, we also found that angular area, increasing it, will lead to higher jet heights, which correlates with our expectations in our general, in our basic theory. So in this presentation, I created a models for both possible jets, including factors such as vorticity, and performed a controlled experimental campaign, achieved predicted agreement results. So for maximum height, we expect that increasing velocity and angular area, we will get a maximum possible height. Thank you very much.
Thank you so much. Okay, so it's time for questions of opponent. 2 minutes, go ahead.
Did you consider P in your flow equation for
Five,
all water even splash?
Sorry?
That phi for splash?
Splash, I didn't consider it because it's not part of the problem formation.
But the first jet is from splash, no?
The first jet is from the focusing inward to the inner radius. Splash was the...
did you consider other factors like density of the wing, the mass of the wing, the height?
Yes, because height directly influences the speed and density influences the mass.
Is there graphs for it?
I have all my written data here, if you would like to look at it.
Okay. Okay. Can you upload that again?
Yeah.
So, how many tries did you use for each wing?
5.
5 tries for each.
5 tries.
Okay. Did you prove theoretically that is first jet always higher than second? Always.
Theoretically, there are extreme cases where the second jet are higher, but for my experiments, I focus solely on the first
So you
jet.
struggle. In your simulation, what did you control it, and what method did you use for simulate?
Well, I used the Basilisk program using C to program it.
So there were viscosity and other.
Yeah, I used
And have you considered time, like ring motion in water, the wave propagation and so on?
You mean if I
Consider time,
like
or just energy?
energy? I want
All
energy.
energy. Okay. When all those energy go at the coefficient?
Not sure. Shortly.
Mostly to wave reflections.
Okay, thank you. So it's time for you to prepare. Okay, time is over, so the floor is yours for 4 minutes and the rest of the discussion, go ahead.
Hello everyone, my name is Jahan Harijan. I'm opposing the third problem ring founding. The problem statement is already said, so I will go on for reporter's report. So what do they do? That the start from the best, they outline the distinction between the investigated jet and working the jet, so they really understand what they own the process and divide it into distinct two parts. And they build simulation of the jet on C. They implemented the vessel function. They showed how do they solve considering viscosity and all the parameters. And also they accounted for the viscosity in simulation. They varied multiple parameters, spring, geometry, drop height, aside for understood. And they have arrived the non-dimensional numbers, and they had clean experiment that showed that the fall of the ring was horizontal and clean without any much errors, problems in it. So, but didn't wish the board to measure the experimental setup. They only showed once and did not vary. They did not show the rings to show, and it was a bit blurred. And they unclear the rules are more stable, could use the release mechanism. Also, they use that phi coefficient, the phi. So they all base their all solution on energy, which is not a bit superficial. And there was no qualitative explanation of their formula of the result. Only that those experimental results without explanation of why that parameters affect why aspect ratio of the radius is important and stuff. And in the last they showed the table and they increased the radius by 2 times, but the thickness was increased only by 1.5, which they changed the thickness while changing the scale. So it's not clear. Changing of parameters, it's very serious for a result. And also they encourage answer to the observation why only consider splash in the center, but they're using phi for splash is not correct because it's not continuous flow, it's in air. Also they did not show that the jet is jet, not the droplets. So they did not show how did they track, what did they track. So there was only per experimental results. Also the implications of the phi in theoretical model. For discussion, we would use the implications of the phi in theoretical model that they showed, the main equations they used. And for discussion, the influence of the tank sizes of the jet formation, because it's important that there could be reflections. And further, I would discuss the movement in the jet. Further, since we have time, the main disadvantage that they do not consider time, the flow, the motion of the ring. Further, they only use the energy of the with coefficients of efficiency. So they did not prove that the velocity and that omega is linear proportional to the first velocity of the ring. And also they did not prove that the second jet is higher than first, but although they tried to show that experimentally and did not consider why there was a contradiction between experiment and theory, which is very important. Okay. Also they integrated some parameters such as density of the ring, the corners, they neglected
Okay, it's a
the
time
height
for
and stuff.
discussion.
So for discussion.
Yes,
Let's start off.
Go ahead.
Okay. I mean, we can show it here. So what's your main formula for phi?
Phi. I can show you.
For flow, the integral. Right. Let's say this.
Yeah, sure, you can. It's up to you.
So
see the first jet. Yeah. I'm sorry. But I use the standard Hankel representation to describe the function phi in my.
So what is the meaning of it?
I use the okay, but it's basically showing the weight, how the weights are affected by
Can we just write it on the desk?
like formula.
Yeah. So, what does the T mean here?
Phi is the velocity field for the irrotational flow in the system.
So, velocity field for the tank, water tank. So, how did you evaluate for finding your result?
Well, I have it in my appendix. So for the calculation of the, basically set the speed, considering this this function phi, as only the water affected by the angular area that is impacting the water surface. And then from that, I should find the Hankel transform of this angular profile over find this function k of k, which is a which is a coefficient of this Hankel transform. I would find that it's linear with.
So it's
the
only
effect-
for
the velocity.
what time?
And at the instant of impact.
At the instant of impact, but at the instant there's only wind and the water did not move yet, right?
Well, it is affected by it.
It is affected, but
So we get an initial velocity of the water surrounding the rim.
but the initial velocity, how did you move from velocity to the height?
Well, velocity is if I get the initial velocity of the jet, I can
So
get the height of the.
the ring is annular, right?
Yes.
So you found velocity of where?
The velocity of the surrounding water impacted by the jet. So that is the effective velocity of the water. Yeah.
So volume.
Yeah, like the water affected by this angular area of the rim.
Okay, but from that you move.
Yeah.
Okay, that ring also shrinks. Since it shrinks, the radius and from the incompressibility of the water, it also shrinks, and all the
Well, yes,
velocities
there's
also
a
are down.
focusing of water going inwards,
So,
which is the main cause of the
did you show that the focus of the water?
Yes, that is directly shown by this graph, right here. Since we increased the angular area of the ring and found that the jet height is increased.
So it's experimental data from annual area and first jet height, right?
And for sure.
But we're talking about theory.
Well, yeah, but here I just want to show you a positive
I mean,
explanation.
there's very little connection between pi or omega you found and the concentration, the height.
Omega is the speed. The effective velocity that I found through this time representation is then I use that to find the speed of the first jet using impulse.
Impulse, but the further motion is also important. Because if we find the initial velocity, we need to consider further how that velocity evolve depending on the parameters.
Yes.
And we moved it to experimental directly.
Well, quantitatively, if we look at the first jet, we find correlation with different parameters such as.
Okay, again, experimental. Let's move on. Also, I want to ask, how did you track the motion of the jet?
Through video.
So, what did you track?
The height. I showed
At
it
what
in my-
point?
at the highest maximum height of the jet.
But the water also those into droplets.
Yeah, really,
I
it's
think-
not a breakup.
So, do you consider when does the droplet goes? And if you check this, then it's a bit out from the state.
Well, when the jet propagates upward, it becomes like small droplets as such. These breakups give a forward momentum of this one, and also like pushing away.
The problem stated the following, and you should have stated that you're exactly tracking the droplet or the jet.
Well, I believe you can't put this included in the description of the top, definition of it.
So you should have
Because it is water.
Yeah, stated in your
Property.
presentation. Right, stated we doing tracking this. Sorry, not this. Okay, that's okay. How does the Can we talk about the Weber's number?
The Weber's number, yeah.
Okay.
It's between 100 and 600 for my surface.
So what does it mean?
It means that surface tension is basically negligible, as it is much higher than 1.
But the surface tension is negligible, then the droplets are also.
No, surface tension for the initial speed I'm finding in my formula.
So
because I'm looking at Weber's number when of the impact of the ring.
that correlation is for like perfectly tension.
I'm not looking at Weber's number for the fountain. I'm looking at Weber's number of the ring impacting the
But
water.
if the problem states that it is you need to consider the mass and height of the jet, not this initial velocity.
So this regime math that I'm using is validate my assumptions in my theory. And my theory does not look at the form of the jet. It looks at the initial speed contributed by the different ring parameters.
I mean, if it did not break into jets, the height would be significantly higher.
That's debatable because these ring breakups called both upward extra speed and extra speed down.
Yeah. So you say that you derive Reynolds number.
Reynolds number. I mean, yeah, you can see that here. It's
How did you derive it?
I didn't vary it in its a very different ring parameters and the different differentiation in the Reynolds number are simply coincidental. Or like they come from the different ring parameters that I use in my experiments. So I did not solely look at the Reynolds number as the impact of the equation.
So if the Reynolds number is very low, you need to state that in your theoretical model,
well,
you show that
we
motion
don't need
is
Reynolds
like this, continuous. But if the Reynolds number is too little, there is swirling here, so our model breaks.
Well, how do you quantify the low Reynolds number? Because they were all 20,000 to 60,000 in my experiment.
So in your theory, it's again, is it experimental?
This is experimental.
So if you use that formula in your theory, you need to validate that parameter, 8 parameters you found are this, not just living and forget it. Do you agree?
I don't find
Okay, let's move to the tank sizes.
Yeah.
So, what do you consider that the tank is also not infinite? What was your boundary conditions that solving in the simulation and the 3D integral?
They were infinite in the simulations. But the thing is that experimentally I found that varying, because I had a 100 liter and 200 liter tank, I didn't find any difference between different heights.
So it kind of reflect waves, right? Also, moving on, the rings is 90 degree.
But I still found a correlation between theory and experiments, which shows that my tank was big enough to neglect these small errors.
Okay, thank you. Time is over, so it's a minute for you to conclude. Opponent.
So first thing first, we talked about the limitation of the theory. So they made the theory on phi, the dot integral equals, and that from that theory they conducted. But in discussion we've talked about why those theory may fail, from the Weber's number, Reynolds number, the swiveling, the motion, the time, the kinematics, which I think are very possible that made their theory very weak, because there are also the limitations that further we talked about the simulation, how to simulate. In my advantage, I In my advance, I showed what they made simulations. I showed what they experiment, the theory, the comparison of the jet though, and that disadvantage I showed that it's very little detailization.
Okay. So it's over.
Okay, thanks everyone.
Okay, so the time for a reviewer.
Yeah, so firstly, what cases do you think with a Swervington jet would be higher than
With a very high mass of the ring and a small inner radius.
Opponent agree with this. Okay. Does the opponent agree with what he said about the high mass of the ring? It will create a high Swervington jet. That is going to be higher than the first jet. Do you agree?
It's not always higher, the second jet.
But what do you think would make it higher
The fruits
than
number.
the first one? Okay. So, and then to the reporter, for the analyzed equation, you use A/3, but that assumes that that A/3 assumes that the whole, the entire envelope is calculated. Shouldn't it be half because at the stage of collision,
Which
the added mass one, you use A/3. Yes, it should be 4/3 because you need to half the surface that is in contact.
Well, I got this from theory, so.
Okay, and then what are the boundary conditions of your system for the reconstruction?
Boundary conditions.
Yeah.
Well, I didn't find that the boundary conditions affected it that much. As I saw.
What is the boundary conditions you use to solve that?
In mine.
Okay, but then again for the reporter, for the boundary condition, if you assume the radius of the tank to go to infinity, that means the energy needed to create a ripples over the tank radius would be infinite.
I mean, yeah, but I find that they are negligible because of my experimental.
No, but the boundary condition of tank radius to infinity, it means that the energy used will be infinite.
I solved the
and then for the experimental setup, does the opponent think there will be a better way of releasing it?
The better way to release it will be like magnet.
It moves immediately. Have you observed for the report? Have you observed that for the ring to drop down, does it always fall vertically to the water?
I use all my experiments were with rings falling completely over
Okay.
the water.
And then how did you fit the C geometry? So how
I have graphs for it. I have graphs for it.
No, did you fit it with the experimental?
I fit it with the experimental data.
Okay. And then so you the opponents you talked about the Rayleigh plateau instability and also like it will break up to small droplets. So because of this, do you think the energy conservation does not work?
It does work. It does not work here for the friction and all other factors.
And do you think that the reporters should have tracked the top of the column or the top of the droplet?
Yeah. Or
Which one?
otherwise you just state that
Which
one
one?
is a trick.
Do you think
the jet itself?
Can I comment on this?
Yeah, okay.
Because the entire jet was experienced plateau breakup. So
Okay,
all
and then for the theory in the analysis side, is it the numerical simulation or the?
This simulation was not included in my program, so.
Okay, the time is drawn, so you have 2 minutes to prepare. No, this is 2 minutes preparation for the reviewer. Stop. Check your connection. Take and put again. Take and put again. Okay. Should work.
This is HDMI.
Yeah, it's HDMI.
Yeah, it's over there. Go
Yeah,
ahead.
it's okay, right?
Okay, you have 5 minutes.
No, that's work.
Just do not touch this connection.
Okay, so today I'll be reviewing the ring function. So we believe that because of the quantitative explanation of the ring transformation is not complete, the quantitative explanation of the jet height, the 2 jet heights were somewhat complete, and then the parameter analysis of the jet formation is also somewhat complete. So we believe that the task completion is partly completed. So then let's move on to the reporter summary. So firstly, it quantitatively explains the displacement of the water, the focusing of the water in the middle, and also it explains the hypothesis of the water that forms when the ring goes into contact with the water. And then the brief theory, it used the Buckingham Pi theorem to find out how many dimensional numbers that are used, and then used the Hankel transform of 0 order and also the first order of the Bessel functions, and then also used the geometric focusing method that is getting from experiments. And then for experiment, it uses a hand release pressure setup and also measure the jet height using the camera. And for the analysis, it uses the parity point, which is to show how close the jet height is to the theory line. And then also use the also very different ring sizes, but there's also he only used the qualitative size, small, medium, and large, and also about the whole ratio. So that was one of the improvements that we suggest. And then he also varied the whole ratio, but for the whole ratio data, there was not really the theory line was not picked up on that line, that slide. So then for the strength, we believe that it's a quite strong qualitative theory because it explains how there will be an extra upper flow of water because of the vortex, and also how the momentum of the radial flow of the water focuses on the middle. And then it's also there's therefore a useful analysis of the working index. And then for quantitatively, it measured the height. And then for the analysis, there was the heat map as well. And we believe that the heat map was important to find out what basis of the collision with the water actually is. However, there are some points to improve. So firstly, there's the inconsistent approach because it uses the conservation of momentum in the for the atom mass. So it uses the impact speed and it multiplies by the m over m plus ma. So it's a conservation of momentum. But next, for the second jet, it uses the conservation of energy. We believe that the second jet should also be calculated from the radial flow of the water's momentum in the middle. So then, for the opposition, you noted that there's a poor demonstration of the experimental setup, and also noted that the thickness is not varied, and also the continuous flow model is incorrect. We believe that it might be due to there's some airborne liquid from the ejector sheet. They also noted that they did not consider the time dependency and the first order velocity formula, which we agree. And for discussion, it's mainly focusing on the clarifying of the Hankel transform and also the velocity field phi, and also whether the velocity field actually shows the focus. So then, we believe that some of the strengths that he has would be that would be the analysis of the different stages of the presentation and theory, because it was definitely a lot of stages of theory was covered, and also considered experimental setup here, and then also considered the different aspects of the theory, and then here are some of the discussion and analysis and why and our opinion on that. So the opponent thinks is not really sure about the meaning of phi and whether it was validated experimentally. And the reporter said that the phi is at the moment of impact. The reporter, we believe that it would have been much better if he had explained how the Hankel transform, that is the axis symmetric case, how he derived the condition for it. And then, for the focusing, we believe that the opponent asked whether the radius change will affect the geometric focusing factor and whether this is checked experimentally. And for the reporter, he used the impulse to find the speed of the first jet. We agree with the opponent of this one. The reporter should more clearly demonstrate the effects of ring geometry because it's literally in the problem statements. And then for the experimental setup, we agree with the opponent that it was really unclear how they track the magnets. And therefore, we believe that they should actually track the top of the unbroken jet. And then also the Weber number, for the number, and we agree with the reporter on the Weber number that is kind of changed. And then for some of these points, we believe that Eventual would be a much better releasing mechanism. And we believe that the Dirichlet and also the Neumann condition should be applied using the Bessel function. And finally, we believe that we can fit the Newton's second law to find the radial flow speed and also the momentum transfer for the second Worthington jet to find the pinch height of the radius, pinch height of the whole system as well. And we believe that the same geometry.
Thank you so much. So it's 2 minutes for the reporter to conclude.
Yeah. As I mentioned about the infinite energy being needed for my boundary conditions, but I use Navier-Stokes in my simulations, so I do not believe that this holds true. Also, for the measuring of the jet, the breakup of the jet, of the radial plateau, was examined throughout the whole jet. So if I would only measure this top unbroken jet, it would be very close to the surface. So, and I do believe that the definition of the jet includes these dropping breakups. Now, for the qualitative size of error that you mentioned in my presentation, I did show the qualitative experimental data for each ring parameters in my appendix that I showed during my oppositions with Kazakhstan. So it is not just qualitative. Also, for the attack on my different methods of achieving the speed of the different jet speeds, I believe that these different approaches were easier for each the jet, making it easier to follow in my presentation. As I believe that using the same method would not really work the same in both cases. Oh, and also for my simulation, I didn't achieve time to mention that. Oh yeah, and you also meant the opponent also mentioned that I did not use thickness singularly proportionally, meaning that I did not vary thickness alone throughout all my rings, but I did not use these differences in thicknesses quantitatively in my presentation. So I don't believe that that attack is valid, as I did not use it for any validations. Thank you very much.
Okay, thank you so much. That's a good moment to thank all the players. And then we have 5 minutes for a jury question, so I'm opening this stage. So, jury, if you have any question, just raise your hand and then we will go on. So, Brian.
For your irrotational part of your velocity flow, you use this Hankel representation in terms of you use this Hankel representation of integral over Bessel functions.
Yeah.
What role did this play in your analysis?
Well, it did show errors since this integral that I basically got from this became close to 0 at the center of the ring. So I did use a more of a ballistic approach later on to describe this first jet.
Okay, thank you.
Okay. Any further questions? Apostolos?
Adam, hi. I want to ask you about some numbers. What was the variation for the initial high of the drop of the ring?
You can see that in my comparison between the first and second jet height.
No, not the height, the ring. The ring. You
Height.
dropped it from which height?
Yeah, these are the different drop heights over
So,
jet height.
Maximum
Maximum was
0.6
around 60 centimeters.
And what was the maximum height?
1.5 something meters. And this was for the first range.
Okay.
Okay, yeah. Any further questions? Go ahead,
I want you to give me like a 1-sentence explanation, each one of you, for this question. There's a lot of discussion about whether you're using the top droplet as the jet height or the top of the column. Reporter, give me 1-sentence explanation why we should use the top droplet.
Because I believe that the definition of jet includes these top droplets, as they are water, in a sense, they're
Opponent?
droplets.
You,
The
you-
same- the
you
same.
were claiming that the top of the unbroken jet was the top. Why is that the top of the jet? Yeah.
Yes, yes.
Oh, we did not consider the top, the droplet, because the problem says jet is some continuous flow of something, not the drop or spheres going physically. And if you use the droplet, you should consider the theoretical, but his theory was on jet, so then track the jet.
Was your answer different from your opponent's?
I would like to add something on that. So ideally, I think they should measure the top of the water droplets, but that is impossible because the water droplets will fragment a lot. So that means that in the experimental setup, the camera may not pick up on the jet.
No, I think that's enough.
Okay. Any further questions of that?
Could you show one video you track from one experiment?
Yeah. I have the first demonstration here in the beginning. My initial observations. And to be clear, I did not use this video to calculate the maximum height.
But you have one where you show the track and the calculations. You have one of this to show.
I do not have statistical tracking data for it.
Okay, thank you.
If we have time, I have one more.
Okay, go ahead.
For the opponent, you said that he should have validated his Reynolds numbers. How would you validate those Reynolds numbers?
So it's not for experiment, but theory, just make some, like the 10 to the some power, just find that Reynolds number is very high, is very low, and use it. Why does that theory work? So I would find some experimental values, like it not exceed 10 meters per second. So Reynolds number is around 1,000, 2,000, so it's very high or low.
Okay, one more question over there. We still have like half a minute.
Okay, for the reporter.
Sure.
Did you use the simulation to compare with your experiments? Or
No,
just
it was
the-
only positive.
What?
It was only positive to demonstrate these effects more clearly.
Okay, I think we can conclude this.
Go,
The jury.
go please to slide 46.
Okay, so shortly.
Yeah. I just wanted to see. Okay, we don't have time.
Okay, thank you so much. So we need some